Hey guys, it's Mr. Sheeling here. I was just kind of going through I was going through my keys and I was looking at the Law of Universal Gravitation worksheet number 2 and thought there's maybe a couple questions that I didn't really clarify to you guys that I really should have clarified. So I'm going to go through just number 3 with you, just to really help you better understand what the equation, like that little g is equal to big G times big M divided by R squared, kind of give you an idea of how to use that. So we're going to go through number 3 here on the Law of Universal Gravitation worksheet number 2. So looking at that question, it says if Pete, who has a mass of 90 kilograms, weighs himself and finds that he weighs 30 pounds, how far away from the surface of the Earth is he? Okay, now this isn't terribly obvious of how to calculate this, okay? So here is what we should do. So what we should do is we should recognize that we are given a decent number of variables here. So we're first given Pete's mass, and Pete's mass is going to be 90 kilograms. And not only that, we're also given his weight. So technically speaking, this is going to be his F of G, which is 30 pounds. Now, of course, we've got to change this, though, because we can't use pounds. We need to have this in newtons. So a quick little Google conversion gives us this, or at least, here, let me double check, because this is from my old key. So let me double check here. So I'm going to put in pounds to newtons. So this dude has 30 pounds. So 30 pounds. Yeah, so that's still good. So that gives them roughly about 133.4 newtons worth of weight. Okay. We're also on, or at least we're using Earth. So the mass of Earth here, we do have that at the top. So 5.98 times 10 to the 24th kilograms. We're trying to find out what R is. How far apart are they from one another? Okay. So the first thing we need to do is we need to establish how it is that a guy that has 90 kilograms only weighs 30 pounds. Okay, because if we were to quickly just kind of put this together, if we were to say, well, on the surface of the Earth, it would be 90 times 9.8. Okay, and this dude in newtons would have roughly 90 times 9.8. Roughly speaking, this guy would have 882 newtons worth of weight on the surface of the Earth, but somehow only has 133.4 newtons worth of weight at whatever distance he is away from the Earth. So we've got to figure out just how far away he is from the surface of the Earth in this problem. So the first thing we need to do is we need to find out what G is. Find G. What is G at the distance he's at? So in order to do that, we're going to take this guy's F of G, and we're just going to set it to this. We're going to set it to just F of G is equal to mg, m times g, which will just, because we're looking for this G, because we've got this and we've got this, but we don't have this. So that'll be G is equal to F of G divided by m. So it looks like it's going to be this 133.4 newtons divided by his 90 kilograms. So it looks like at this distance, at whatever it is, he's experienced something like 1.48 meters per second squared. So this isn't the answer clearly, but this is the amount of G's that he's feeling at this distance, okay? So this is where then we use this equation that I just slapped onto this worksheet really with no explanation, okay? So here we're going to use this G. So force of gravity or acceleration due to gravity is equal to big G times big M divided by R squared. Yeah, R squared. So where does this derivation come from? Basically, this derivation just comes from some trick work where we eliminate, I guess here, to show it real quick. So the force of gravity felt, using this equation here, felt between mass of 1, mass of 2. Okay, it's basically this, that if we want to, we want to find out what the gravitational force is between them, we're going to divide this to both sides. So if we were to divide the mass of our guy here on both sides, what we're left with here is we're left with just g, because of course f of g divided by m2 is going to give us g all by itself, and then it gives us this. It just leaves it to this. So that's how we get this equation real quick, okay? That's how we get this equation. We factor out basically this guy, and in the process of factoring out the mass of the object that we're trying to find, we're able to take advantage of the gravitational force he was feeling at whatever distance he was at, which is this right here, or the distance between, okay? Which actually would be the center of mass to center of mass. So this is the distance from the center of the Earth to the center of mass of our peat. Okay, so we're going to use this formula in order to find this guy. So because we've got this, we have this, and we have this, because this is just the mass of the Earth now. Okay, we need to find this guy. So if we set it to r, it's going to be r is equal to the square root of big G times mass of the Earth divided by g, okay, which is going to turn into this. 6.67 times 10 to the 11th power. Oops, that is a negative 11th power times the mass of the Earth, which is 5.98 times 10 to the 24th. All of that's divided by g, which in this case is 1.48. Okay. So with me so far, we're trying to find, ultimately what we're doing is we're trying to find the distance this guy is from the surface of the Earth. And what this r is going to give us is from the center of the Earth to the center of mass of Peter. Okay, which looks like that's going to give us roughly about this number right here. It's going to give us like this big old number of 164,16578.64 meters. That's what that gives us. So again, this is going to be, if this is Earth right here, okay, so just to crudely draw, oh boy, poor South America, I'm butchering South America here. So to crudely draw, there's Canada, here's the United States, Mexico, Central America, South America, got Europe over there, you got a little bit of Asia over there. Okay, Australia down there. Okay, it's a little warped, but whatever. Here's the Earth. That's the important part. It's the center of Earth to the center of Peter. That's somewhere within the vicinity of the Earth. That's what this number represents right here. From here to here is my R. Okay. So, but the question is asking, how far away is he from the surface of the Earth? Well, he is whatever this is minus this, the radius of the Earth. So it's going to be, and just let's just kind of put this into perspective. This is going to be 1, 2, 3, 4, 5, 6, 7. So just so we have a perspective of size of this. So here is the distance, and then from the center of the Earth to our guy, but then the radius of the Earth, if we look at our chart there, the radius of the Earth is just 6.38 times 10 to the 6th power meters. So it looks like it's going to be this number minus this number, 6.38 times 10 to the 6th power, which gives us a radius here. So from here to here, looks like he is roughly about this number away from the Earth, which when I get it written down, I'll say what it is specifically. So it looks like this guy is 10,036,578.64 meters from the surface of the Earth. Okay, so that's cool. That's our answer right there. And we could really just put 1.0 times 10 to the 7th power meters for our answer. Okay, that's the distance that he is from the surface of the Earth all the way out there. So it's actually quite incredible how much gravity he's feeling that far away from the surface of the Earth. Okay, so that would be the answer, but let's say you're not happy with that answer. Let's say that you are like, that just seems so strange. How is that possible? How could it be that that guy was feeling that kind of, how could he be feeling that kind of I guess force all the way that far out? How could he be this far out? I don't trust it. So here's how you can double check that answer. This is really what I'm babbling about here. Let's double check that answer, and let's just see what we get. So let's use what we've been using. Let's say we don't know what this is. We don't know what F is. But we got G. We've got M1. We've got M2. And now we've got this. Okay? We do have this. This is not going, it's not going to be the number we just got. It's not going to be this number, okay? Because remember, this is from here to here, but we definitely have this number. We've got here to here. That's this number right here. Okay? So, this number from the center of the Earth to the center of our mass is going to be this. And let's just see what we get. So it'll be F is equal to big G, which is 6.67 times 10 to the negative 11th power times the mass of our Peter, or of Peter, let's just say Peter, it sounds weird, times the mass of the Earth, which is 5.98 times 10 to the 24th power, all of that divided by our 16578.64 times squared. Let's just see what we get real quick. Let's see if I pop that in my calculator. Let's see what I get. So 6.67 times 10 to the negative 11th power times 90 times 5.98 times 10 to the 24th power. All of that on top divided by 164,16578.64 squared. Oh, don't do that. Oh, come on, don't do that. 16578.64. And we get 133. What did I hold up here? Is that how I found it? Oh, hold up. Your boy is now. Let's see. That's not how I need to double check that. Sorry, here, give me a second, guys. Recollecting my thoughts to double check on this. I got something I don't remember ever getting. So here's what we would get there. 133. Was it? Oh, that's why it's important. It's because if we wanted to double check, the force felt between these two objects, we get this 133.2. And what that gives us is that gives us the amount of weight that our 90 kilogram object would be feeling due to that force. Okay, so what we just found here is this 133.2, which is off by just 2/10 here. Okay, this is the force felt between the two objects, but it's also the force of our object, our Pete, out at this particular distance away from the center of the Earth. Okay, now let's see, and how to convince you otherwise, because again, it's not obvious that the weight that the guy is measured in, the 90 kilograms, is the same as the force felt between the two objects. That's not terribly obvious either. So let's maybe, how else to convince you? Because I mean, if we think about it real quick, if we've got a dude, there is a force between the Earth and the dude, and they're going to be the same amount of force between them. But arguably, obviously, the Earth is not going to wobble as much as we are, or Pete is going to wobble because Pete's mass is quite less, but the force is still the same. Oh, it makes sense to me, but still not obvious to you, maybe. So if you're done with the video, because now this is stream of consciousness right now, you can go ahead and turn this off, but I'm going to still try to convince you here. So if you got what you needed out of this video, you can go ahead and leave. But I'm still going to try to carry this out to really convince you that this is what it is. So again, because what we just found here is the force felt between the two objects, which should be the same as the amount of force felt that we could measure off of our 90 kilogram guy here. Okay. So here, what I want to do is I want to show you that it is 1.48 meters per second squared felt between, or that this guy is or that's being exerted on the guy. Oh, shoot. I'm trying to think here. I guess that would be it. So, okay. I guess I really just have to hammer that home. Let's think about this real quick. So the force of weight felt and exerted on, or that the guy is technically pulling down on. So if we've got Pete out here, right? We have Earth down here. Pete, in reference to the Earth, has an attractive force towards the Earth. The Earth has an equal attractive force towards Pete. And it's some sort of F of G here that we can calculate using the big G, the mass of this guy, mass of this, and then the distance between them, Okay. So how is it that the weight that this guy exerts is the same? How is it the same as the force felt between them? So again, remember, this guy has a mass of just 90 kilograms. The Earth, has a mass of specifically, where did it go? 5.98 times 10 to the 24th kilograms. So what is going to wobble more? Clearly, the Earth is not going to wobble as much as Pete is going to wobble. And we use the term wobble just as like who's going to be affected. Yes, we do have an effect on the Earth, but realistically speaking, the amount of force, though it is the same, who comes out and has a bigger impact on the shared force between the two objects? It's going to be the one that has a higher mass. So how is it still, though, that the force due to gravity felt between them is the same as the weight, the force of weight on the guy? And the best I can say is because the Earth has more mass, the wobble of the guy is going to be more, and the wobble that we observe in the dude is the force between them, which is also going to be the weight. And God, that sounds so confusing, but that's what it is. So how do we double check our work past of what I just figured for you? Well, it's this. Okay, it's that we take the 133 newtons F of G that we just calculated right here. We take this number right here. And we're going to take the the mass of our guy, of our Peter here, which is 90, and we're going to divide that and see what we get. We should already know what we get, but just to double check here, we get 1.48. We would get this. And because we divided our newtons by kilograms, which remember, newtons is just this. Newton is just kilograms by meters per second squared. Okay, so really it would be like kilograms by meters per second squared here. So kilograms would cancel out. We'd be left with meters per second. So 133.2 divided by 90 gives us 1.48 meters per second squared. Exactly the G that we calculated before, taking the weight of our guy and dividing it by the mass, 90 kilograms, to get this. Okay. So to double check our work, that's what we just did. And remember, to be frank about it, what is our weight? Well, our weight is just the force of gravity due to the acceleration of gravity, or in this case, the acceleration of gravity that we're able to calculate. And it's also the shared force that we have between the Earth and our mass, or between the mass of the Earth, the mass of ourselves. It's that force, that attractive force between our two masses, our shared force. There is, in Pete's case, Pete is exerting 133.2 or 133.4 newtons worth of force towards the Earth. The Earth is exerting 133.2 or 133.4 newtons back to Pete. It's a shared equal force, but of course, again, Pete is more affected by this than the Earth is. Blah, bitty, blah, bitty, blah. There's nothing else I could really do to convince you otherwise. That's how we would double check this. Ultimately, what this video was concerned with was just showing you how it is that we can get this number. So if we've forgotten all about that, try to go back a little bit and see how it is that we get this number. So thank you guys if you kept watching this video. I appreciate you watching this video. If you still have any questions, if you want me to walk through it even more, I can do that, or I can point you in the right direction to figure out how it is that, basically to explain this part. If you want a better explanation, I can point you to a better explanation of how this is possible, how it is that they're the same, or at least similar here. I can definitely do that. But if not, then I'll just see you in the next one.